So today we're going to wrap up this thing about particles moving around in space. And I'm going to wrap it up by just showing you some stuff in MATLAB. Then we're going to go on to pulleys, which is a beginning of a new topic, and I'll try and explain sort of the organization of the course in terms of what's new and how what's the new idea. And then I wanted to show you a collision demo. Let me just start with the collision demo. I forgot to do this before. Here's a ball that bounces, and it comes up not quite as high. It comes up not quite as high because the velocity when it separates is less than the velocity when it approaches. We assume that's a material property. That's actually a bad model. It's not really a material property at all because, for example, it's not a property of the table and the ball because this ball bounces better in one spot than in another spot. And like the tennis court material I showed you, just little details make a big difference. But still, that's an approximation people make, that there is such a thing as a coefficient of restitution. It's a bad approximation. Now, there's also a coefficient of restitution between one ball and another ball. And then you get this funny result if you drop two balls on top of each other, which was a homework problem, which I meant to demonstrate for you, like that. So I just dropped this a little bit, and that drops. And if I'm coordinated, which I'm not, I can do three like this. And you say, well, why does it do such a huge dramatic thing? Is it that the coefficient of restitution of the ping pong ball is big? No. These have a coefficient of restitution of less than 1, and that has less than 1, and that has less than 1. It's that there's a sequence of collisions. This goes down, bounces up. Now this is going up. These are approaching each other. Then after they bounce, they separate. They don't their relative separation speed is less than their approach speed, but this is already going up. So this goes fast. And now this is going fast. This is still going down. Then they're approaching at some relative speed, separate at less than that speed, but this is much heavier than that. So the motion is this big motion. And then you can do it with 4 balls. And here's a toy with 4 balls lined up like this. Ready? So you get a dramatic effect. Okay, any questions about that demo? Okay, so then I want to show you some MATLAB stuff. As far as lights go, we wanted to get the house lights front, down. And it's those blackboard lights that we want to get off, right? How about that? Good? Any problems with the lighting? Okay, so we had this problem that I've showed you a couple times now, which is a satellite going around the Earth, something like that. We set this up as one big file to start with, and then I've showed you to break it into 3 files. One which sets up the problem here, another which tells you what the differential equations are, and this is nothing but the differential equations for a particle going around the sun, Earth going around the sun. And here are the differential equations, and everything else is just unpacking and packing. So we have 2 files, and then the third file is this Euler method, which is a general purpose solver of differential equations, all of Math 293, and basically it's all of Math 293 in this one line here. Okay, any questions about that? In the back, do you have a trouble with the font size? How about come to the front? Lots of space up here. Okay, so we have this broken into 3 files. The price we pay for that is that we have to keep track of file names. For example, this general purpose solver solves something called right-hand side, but right-hand side is actually this thing in the satellite right-hand side. So we had to pass in to the solver the name of the place where the differential equation was. So in our program that solved, this is our main driver, which sets up the problem, then asked the differential equation solver to solve. We had to pass in the name of the file where the differential equation was. That got passed in, called right-hand side, and so on. Okay. Now, we run this thing, and it runs with such and such accuracy. Let's just see how it goes here with 1,000 points. And the main thing is we see that we get, if we have the right initial conditions, we get these closed orbits. In fact, for any initial condition, it turns out for this planetary motion, you get closed orbits. Always an ellipse with the focus at the center, not the center of the ellipse at the center. And that's this classical planetary motion stuff, which your program will just give out without knowing anything about ellipses. Now, if I pick, this one is accurate because I didn't use my Euler method, and I used the method I want to show you next. So here's the Euler method. I run it with 1,000 points, and what did I get, an error? Because it's called Euler method 1, I think. There. So I have a not so accurate solution. It should be a closed orbit if it was exact, but with 1,000 points it didn't come out exact. So what I've done here is because this particular problem conserves energy, I can check the solution and see if it conserves energy. So all the way through the solution, I can check the radius. Here's the radius. I can look at the speed squared, and I can calculate the kinetic energy and the potential energy, which actually there should be an M1 here, M2 times this thing. I can look at the total energy of the system as a function of time, and I can take the error to be the difference between the maximum and the minimum divided by the initial. It should be constant. This number should be 0. So when I run this thing, I get this output, which is back here on this screen, which says the error is 0.1007. The energy changed by 1 part in 10, 0.1. And we can see that there's an error because we know in this particular case we should get a closed orbit here. If we make it more accurate with 10,000 points and run this again, then we get more of a closed circle, and we see how big the error is, and it dropped down to 15 parts in 100, 0.015. And I can make it more accurate still, 100,000 points, 100,000, 100,000 points, and I run this, and it's still thinking, it's getting slow, and then starting at, it's still not done. And then I got my error is 0.0015, 15 parts per thousand, and I look at the figure and it looks like a pretty good circle. So the more points I pick. Now let me show you a different way to set up these differential equations, which is to set up the solution. So let's take as an example problem a really simple differential equation, x dot equals t. Now, if we had this example, we know that the exact solution by pencil and paper is that x of t is equal to some x0 plus t squared over 2. All the solutions of this, if we did it with pencil and paper, are like that. So we could plot all the solutions as a function of time like this. Here's x, and we have one solution looks like so. And then there's another solution that looks like so, and another solution that looks like so, and another solution looks like so. So these are all the solutions of this differential equation. And if we want to know which solution we're on, we look at what initial condition we're on here. Now, if we used Euler method to solve this thing, what would the solution be? So let's just pick this as our x0. And Euler method right here gives us a slope of 0. We take a step, and we get to this point. Then we look at the slope at this point. We take a step, and we get to this point. Then we look at the slope at this point, we take a step, and we go like so. And here's the exact solutions. And here's the Euler method solutions. And you can see it takes the corners wide. Any questions about that, this Euler solution? This is what we're doing with Euler's method, is you take a step and you use that to predict the future, and you don't quite predict it accurately. The smaller the step we pick, the more accurate it will be. So this idea that I'd like to show you is a better method, and it's one of a whole sequence of better methods. This is the one that I ended up using in my PhD thesis because it was the one in the book that said all methods converge very quickly except for Euler's method. So I went and looked at the dumbest method I could find, and this one works really well, and I'm going to show it to you. So what you do is you start here. And you want to take a step out to here, a big step, but you take half a step. You evaluate the slope at this point, and then you use that slope to take a full step. So you take this slope and use it at this point. So you take half a step over to here, measure the slope, and then use that to take a full step. And you see it comes up much closer. Then we take, at this point, we take half a, here we know the slope, we take half a step, it takes us to here. We measure that slope, which is very close to what we want, and then we take a full step, and it comes out not exact, but much closer. Okay, and that you could call the midpoint method. It's also called Runge-Kutta 2 method. Runge and Kutta are two smart people who thought about how to solve differential equations. It's a more accurate way to solve the differential equations. So let me show you how that looks on the computer. Questions about that on the blackboard? Yes?
I'm familiar with something called the improved Euler's method. Is this like
This might be, I don't know, this might be called improved Euler method also.
okay?
I don't know what improved Euler method is. There are a bunch of methods that are in the neighborhood of this. Another method that's like this is you take a full step, take that slope, and use the average of the two to take a full provisional step, measure the slope, and then take the average of that and the original slope to take your real step. I don't know. That might be called improved Euler method. I don't know. Yes?
The slope that you're taking in the middle, you find it at the average of the x values between the 2 points?
You start here, you take half a time step, and you don't know, and you see wherever that takes you. Now remember, z could be, here I have x, but x could be x, y, z, vx, vy, v. So you take half of a t-step, use that value, the new value of z you get, calculate the z dot at that point, and then use that z dot to start from here to go to here. And you'll see what the formula looks like in a second. I missed. I can't get the lights right. Podium lights, how about that? Okay. So let's go look at the Euler method we had for solving differential equations. We set up these t arrays and the time step and filled in this blank array, and we figured out the current value, and then the big step in Euler's method was this line here, where we say the new value of z is the old value of z plus the time step times the right-hand side. And that was with this fancy f-eval, which means evaluate the right-hand side, whatever that file is, with the current values of t and z and the parameters. Okay, that's Euler's method. What we're going to do with RK2, this fancier method, is just a slight change in that. So this one is just slightly different from this one. This is just the difference between the two is one line. So what we do is we say, let's look at the current value of z. Let's get a new value of z by taking only half of a time step. So it's the same as Euler's method, but only half a step. Then, with that new value of z, evaluate the right-hand side of the differential equation, multiply by h, and take a full time step. Okay? So that's the whole thing with RK2. So now we can go back to our satellite 2 program. And now, rather than do it with Euler method on 100,000 points, we got this accuracy of almost 1 part in 1,000. Now that we're using RK2, we're going to replace this with RK2, our new RK2 program, which is just slightly different, just that temporary step. How many steps do we have to take to get that accuracy of 1 part in 1,000? Here it took 100,000 steps. Now we're doing twice as much calculations each time we take a step. Seems like a waste. So it better be that we can drop this to at least 50,000. How about 1,000? Try 1,000. 100 times less calculation. Well, only 50 times less calculation. We get this nice looking circle, and we get this error of 1 part in 10,000. 100. We get this nice looking circle, and we get this error it's a little bit bigger there, so let's try 200. So we put 200 instead of having 100,000, and we get about the same size error. So instead of doing 100,000 evaluations of the function, we only do 200. So we change it by a factor of 500 for the same accuracy, just by adding that one line of code. Okay, any questions about that? Yes?
Doesn't every
Right, so it's twice as much effort per step, but we take 500 times fewer steps for the same accuracy. So it's still a gain. And the more accurate you're trying to get, the more you gain. If you're not trying to be accurate at all, then you don't gain very much. And that's why there's all different varieties of methods people get depending on whether they want fast integration or accurate integration and so on. But if you just want to take one dumb method and use it all the time, just use this one I just showed you. Okay, any questions about this? Okay, now let's go to the problem I set up in lecture last time, which I didn't quite finish, which was this two planets problem. So here we have two planets flying around each other. This is straight out of lecture last time. What we had was differential equations. For each planet, we had F equals ma. So F equals ma is a differential equation. It's a bunch of scalar equations. F equals ma for each planet is a bunch of differential equations. For each planet, the rate of change of position is velocity. This is two numbers, or three numbers if it was 3D. Here's two more, 3 and 3D. We have the attraction of one planet to the other and the attraction of the other planet to the one. This is basically F equals ma in here. And then we can run this two planets driver. So, and I'm using now my RK2 method. And this is just setting up the initial conditions and so on up here. And then I can see how these two planets move around. And they move around with the initial conditions I picked. They move, each of them moves in an ellipse. And you can look at position versus time or something like that. It turns out that two planets, if you're clever about how you pick the coordinates, don't move in a way that's any more complicated than one planet. So if you do clever things with pencil and paper, you can reduce the two-planet problem to a one-planet problem. Why is that? Is because the center of mass of the system moves at a constant velocity. So you look at the motion relative to the center of mass, and if you know the velocity of one planet, you know the velocity of the other. So they have to kind of move in mirror images relative to each other in proportion to their masses, or inversely proportional to their masses. So no matter what they do, they kind of move in complementary ways around each other and around the center of mass. In this case, they're equal masses, and it's this common point here. If I picked different masses, I would get they would have relatively different motions, but they still move in sort of mirror images relative to each other. One does one thing, the other does the other. It looks like I have a little bit of error here. Okay. Actually, you can't, it's relative to each other, relative to the center of mass. And if this particular initial condition, the whole problem is going to drift off to the side because I have the center of mass having some constant velocity. So you can't see the mirror motion necessarily very clearly. They're on their way out to infinity somewhere. Okay, I don't want to think about that in any detail. The point is that if you have, and this is like the capstone of this part of the course. So right now I'm at the capstone of the course so far, which is that if I have a particle and I know that it satisfies the laws of mechanics, F equals ma, and I have rules for what the forces are, I either tell you what the force is or I tell you a rule that tells you the force in terms of the position and the velocity, then I can figure out how that particle moves. And if I have another particle and I have rules, I can see how that moves. And if I have two particles, I can see how they both move. So if I think of the world as made out of particles, all you do is add more and more terms to that list of z variables in your differential equations, and you can integrate forward in time and see how things move. So if you think of the world as made of particles, and the laws of physics as being laws that tell you what the forces are between them, springs, dashpots, inverse gravity attraction, you can just set up the differential equations and solve them, and in principle you can do all mechanics problems at this point in the class. So you do 2 particles, you could do 3 particles, you could do 4, then you could do 50, you could do 500, and so on. So in some sense we could end the course right here if you were willing to think of the world as made of atoms with laws of interaction and you had a big enough computer to set things up and solve them. For example, if you thought of a truss from statics as a bunch of point masses at the corners, and the corners were interacting by a force law, which was the stress-strain relationship, the relationship between force and deflection of a bar, you could put that force law for those two particles And you could find the deformation and forces in a truss using this dynamics problem, using this program. You would set up the truss, you'd put the loads on it, and you would find the truss vibrating around. You look at the positions, calculate the forces, and you could solve the truss this way. It's easier to solve the truss this way than it is to solve it the way we did in 2020. Because we don't have to do any backslash, we don't have to set up any big matrix to invert. We just go forwards in time and look at how the corners move around. Why don't we do that is because if we did that, we'd find the truss vibrating all the time. Well, we could put in a damping term, it wouldn't damp. If we put in the damping term, we could still do it, but then what happens is that we pay in this part of the problem. To get accuracy, we have to do such long integrations that it turns out to be just a slower way to do the problem. But because statics is a subset of dynamics, you can solve every statics problem as a dynamics problem. And dynamics is now easy, so we can do all statics problems in this easy way of doing dynamics problems. Any questions about where we are so far? Who kind of understood what I was just saying? You think you sort of followed it? Raise your hand. Kind of didn't follow? It sounded way abstract. Okay. Questions about it? Did I tell you the Laplace quote? Let me just repeat it if I did. It's in the book, which is he said, if I knew where every atom in the universe was and how fast it was moving, I could predict the future of the universe. And the idea is that if you believe in classical mechanics, that's before quantum mechanics, you know where every atom is, you know all the laws of interaction, you know F equals ma, the laws are determinate, you write a big program like this, you run it, it tells you the future of the universe. And that's sort of the philosophy of our setting up and solving differential equations here. We don't believe we could do it for the whole universe because the computer would have to be bigger than the universe to keep all that information in it. And how can the computer be bigger than the universe and inside the universe? But if we had some other bigger computer on the side, we could do it. But then that's not quite right because of quantum mechanics and so on. But for macroscopic things, we believe that that's true. If you know the state of the system and the rules, you can predict the future. Question, please? Okay, so now I want to go on and do a different problem. Different thing. We're going to go on to a new set of topics. Raise system off. We want this one on. Okay, so if we have particles that are moving around and we know the laws of attraction between them, we can solve all problems, and we can do truss problems too. I said that if we did the truss problem, we could solve it this way, but what happens is the differential equations end up solving for all these vibrations, which take a lot of time to solve accurately, and we don't care about them. So we want to go back to the statics kind of point of view and say there are interactions which are so simple that we don't want to spend time thinking about them in a dynamic sense. And what those kinds of interactions are things that sort of hold together for the most part. So here's this tennis ball. I could simulate this tennis ball by thinking of it's made of 10 to the 23 atoms and all the attractions between them, but somehow it's simpler to think that all the atoms in them are restricted to move relative to each other a certain way, sort of a rigid object. So this idea that some things are restricted to move relative to each other simplifies the problem. We want to bring that into the problem. So what happens is there's a shortcut we want to take. We don't want to look at all the complicated interactions that hold the parts of one thing together. And that shortcut makes thinking about it harder. So that's kind of the rest of the course. The rest of the course is we don't want to think about all the atoms separately. We want to add constraints. That's a shortcut in a calculation sense, but it makes it more complicated for us to think about, and that's what we're doing from now on. So we want to think about what are the forces when things are constrained to move relative to each other certain ways. And so I'm going to start with the simplest class of sort of constrained problems, which are these pulley problems, and then we have more problems coming up on how to think about the forces when things are constrained to move certain ways. Okay, so here's a object we want to pull with this pulley. Assume this is a frictionless table, and I want to use pulleys to pull this object. And there are various ways I can use pulleys to pull this object, and I'm going to set this up on the blackboard. So I have some object here. I'd like to pull it with a pulley. And one way I could pull this with a pulley is I could wrap a pulley around like this, and I could apply a force here like this. And here I'm going to have a force, and here I'm going to have a mass, and here I'm going to have a pulley, and I'm going to anchor this pulley to something like that. And if I want to just be clear that I'm doing a one-dimensional problem, I can set this up like so. Now, there are other ways to try to pull things with pulleys. So I can put a pulley on the object like this. I can anchor some point over here like this. I can wrap something around like this. And then I can pull this with a force like that. And that's a different way to pull something with a pulley. But there are other ways still to pull things with pulleys. I can go like this. And then I can put a pulley over here. I can attach this to the pulley here. I can attach this to the wall here. I can wrap, oops, that looks like the same one again. That's not what I intended to do. I intended to wrap this around to here. Wrap this to a wall like this, put a pulley over here like this, and apply a force here like this. So I can put this one on the ground with wheels, and I can put this one on the ground with wheels, and I have these three ways of pulling things with a pulley. And I can label some points here. I'll call this A, I'll call this B, I'll call this C, I'll call this D, I'll call this E, and I'll call this G. Okay, so I've got problem 1, I've got problem 2, and I've got problem 3. Okay, now they look suspiciously similar to each other. By the end of today, and certainly by the time you do the homework related to this, these should look all very different from each other. But to try to emphasize the point, I'm going to give you a quiz, if I can anyway. I can't give you a quiz because my computer crashed. It doesn't like switching between monitors. Okay. So the quiz goes like this. Let's look at the acceleration of point D. And let's look at the acceleration of point G. And I would like to know the ratio of these two things. And I'm going to give you some choices here. Of course, one of them is none of the above. And let's see, I could go 1 over 16, 1 over 4, 1, 4. No, let's put something wild here, something like that. Okay. So why don't you think about that for a few minutes while my computer starts up. Ask me questions about the question. Yes, student.
What are AP and AG?
What are what?
AP and AG.
AD.
Oh, D.
That's the acceleration of this point. We'll pick a coordinate system off here to the side where x is off like that. And what we mean by acceleration is x double dot. Those are the accelerations of this point and this point. Does that answer your question?
So G is gravity?
Oh,
G is the point G, okay.
Do you want me to label this? Let's call this point H. Okay. More questions? Where's Luke? Is Luke here? My computer guy. Incredibly silent. You guys are practicing for tonight or something? How about talk to your friends? Let's make a little noise here, Micah. Yes? Say again?
Is the poll open?
Is the what open?
Poll.
No, the computer's not running. We're waiting to restart the computer. The computer crashes when I switch monitors. It's a problem. It's 'cause now see if you can vote. Good. Okay, 1 minute more. You want to see how confident you can be about your answer? So I learned this problem from a guy at MIT, and he said, you know, we teach all these students this stuff, and he said, I give students like a pulley and a string and a block, and I ask them, use this pulley to do X, make it go faster, easy, harder to pull or something. He said most students just can't do it. And I sort of thought about it, and I realized that unless you think about it, these problems look incredibly similar to each other, and they're not. And so you want to like somehow look at them or develop the skill to see that these problems are not so similar to each other. Okay, 5 seconds left. Make a guess so at least you register something. 5, 4, 3, 2, 1. Bad attendance in class today. Okay, lock up the vote. Look at what we got here. I think this might be a world's record in my success at getting you to give the wrong answer. Okay, so let's try and figure this out. So let's take one of these problems. Let's take this one here. So we've got a kinematics part to work with, and then we've got the free body diagrams to work with. In this case, we've got to work with both geometry and mechanics. Let's just start with the kinematics. So what I'll do is I'll just copy this problem again, and I'm going to do problem 2 here. And what I have is this pulley here. It's wrapped around like this, and there's this point over here like so, and this comes over here to this wall like so. And I've got this force over here, which I'm not really going to pay attention to now. I called this point here D. I called some point over here C. Let me just call it this point here C to keep things simple. So I'm going to call this point here C. And now I want to keep track of things. So let me just give you advice. When you keep track, put some reference system off to the side. Never put the reference system inside the system. Put it either on the left or the right. And then we've got various distances we've got to keep track of. We've got to keep track of this distance out to C. We've got to keep track of this distance out to D. And we've got to keep track of this distance over to this other wall here. So this distance to this other wall, I can call this L. I can call this thing XD out to this point here, and I can call this point XC. Now, given that, what do we want to do with this information? The key thing is that the length of the string is a constant. So that's the key kinematic assumption, is that the length of the string is a constant. So we want to keep track, what is the length of the string? Well, the length of the string is not this L here. What is it? It's this. We could call this. We give this wall over here on the right a name. We already used H, G. Call this I. Call this over here this origin. So we have the length of the string from here to here, which is xi minus xc. That's that length of string from here to here. And then we have also plus xd minus xc. And then we have also plus pi times the radius of the pulley. And this whole thing is equal to a constant. And this is our basic kinematics equation for this particular pulley problem. Now, some of these things are constants. If we take this expression here, and we take d squared by dt squared of this whole expression, we have xi double dot, but xi is a constant. So we have minus xc double dot plus xd double dot minus xc double dot, and then we have equals 0, because the derivative of this is 0 and the derivative of that is 0. So that tells us that xd double dot is equal to 2 times xc double dot. That means, going back over to this point has twice as much motion as this one does. And if you want to think about that intuitively, here is this problem. Skip that one here. Here's this wall. Here's this thing here. If I pull this point here, this thing moves twice as much as the pulley moves. Why is that? If the pulley moves a little bit, imagine the pulley moves a little bit, this would move just as much, but then there's a slack rope which comes around also. So this point moves twice as much. It has twice the displacement and twice the acceleration. Okay. Now, what if we use the fact that in this free body diagram, we use, like we used in statics, that the tension here is equal to the tension here. So the free body diagram of this thing with this pulley, we have an F here, and we have an F here. So F equals ma. In this case, it's a scalar equation. Tells us that the sum of forces equal, not to be confused with that F and that F, tells us that 2F is equal to the mass times the acceleration. That's the acceleration of point C. So it says that the acceleration of point C is equal to 2F over m. And that then tells us that the acceleration of point D, if we put this together with it, is equal to 4F over m. So for this problem, the acceleration of this point is 4F over m. Let's just try and get that intuitively. This is this problem here. This one is anchored, and I'm going to pull on this one. When I pull on this, there's a tension in this. There's also a tension here. So the force on this mass is twice the force I'm applying. But the motion of this point is twice the motion of this point. So this has an acceleration of 2F over m, and this has an acceleration of 4F over m. Okay. Now, let's look at that other problem, which looks surprisingly similar, but is really quite different. And we draw all the same pictures and do all the same analysis. This thing wraps around like this. It's connected to this block here like this. We have this pulley here like this. We're going to pull this over here like this. And we're going to keep track of these points. Let's call that middle point there. Just to keep it simple, I'll keep track of this point here and call it H. I could add another length to it, but I'm just going to cheat here. And then I'm going to call this point here, what did I call it? E. And now I want to keep track of various positions and so on. So I'm going to measure from here over to here to point E. And I'm going to measure over here to the center of this thing. So this is going to be XE. Here's going to be XH. And then my kinematics, which is I'll use the same reasoning again, that the length of the string is constant. And see, what is the length of the string? Well, the length of the string is XH minus XE. That's this piece of length, and then I have plus XH. And then I have plus pi times the radius is equal to a constant. I take this expression here. Here, let you look at it. In fact, why don't you look at it and make sure you're happy with that and ask a question about it before I go on. So, somebody asked a question about it? Yes?
On the previous problem,
Yeah.
where we drew the free body diagram with the block and the pulley,
Yes?
doesn't the pulley itself turn when you pull the string? So how can the force be equal on both sides?
Okay, that's a good question. So, our assumption about pulleys at this point in the class is that they have negligible mass. And because they have negligible mass, we treat the pulleys as if they're a statics problem. Right? So certainly it takes, to rotate a basketball, it takes some force. It doesn't take very much. And we assume that the amount of the difference between the tension on this side and rotate the pulley is negligible. So it's the ideal massless pulley. Does that address your question?
Yeah.
Yes?
On the previous one, I'm a little bit confused
how you went from the first equation with constant to the second derivative.
How did I get from here to here?
We'll go from the top, very top of this to that one.
This equation, are you happy with or no? This one you're wondering about?
Yeah, how you got
From here to here. So I want to take the second derivative of this expression. It's the sum of terms. The derivative of a sum is the sum of the derivatives. xi is the distance from that wall to this wall. It doesn't change in time, so that term drops out when I take its derivative. And likewise, the radius of the pulley is constant. It drops out, and all that's left is these three terms, which show up here. Does that address your question? Okay, so now we take this expression. We take second time derivative of it, set it equal to 0. We have xh, xe, so we have 2xh double dot minus xe double dot is equal to 0. So it says xe double dot, or xh double dot is our object of interest, is equal to xe double dot divided by 2. Now if we look at linear momentum balance, first of all we draw a free body diagram. The free body diagram has, when we look at it, we have a tension here. That's not the only free body diagram we want to draw. We also draw a free body diagram of the pulley here. And it has a force, and it has a tension, and it has a tension. So this tells us that the tension is equal to the force divided by 2. And then if we use linear momentum balance, which says that the sum of the forces on the block is equal to ma, it says that the tension is equal to ma. It says that F over 2 is equal to m times the acceleration of point E. So it says that the acceleration of point E is equal to F over 2m. And then that tells us that the acceleration of point H is equal to F over 4m. Okay, so now let's try and do that intuitively. This is this different pulley arrangement where I mount this to a wall and I'm going to pull this way. Now I pull on this pulley with some force. First I look at what's happening at this pulley. This pulley we think of as altogether massless. So we just do statics on the pulley, not just for rotation but also for acceleration. Therefore, this tension and this tension, which are equal to each other by sum of moments about the center of the pulley, assuming good frictionless bearings and a round pulley and all that, this tension is equal to this tension, which therefore is half of this force. So only half of this force gets into this string. So here we have half of the force, so this only accelerates with F over 2m. But this thing only moves half as much as this does. How do I see that? Well, if I imagine this block moving a little bit, there it moves. This can't go without giving up that string. Or another way to say it, if this is going to move a little bit, it goes, this has to follow along, it pays out this string, but that string has to come in. So the motion of this is the motion of this plus the string which is paid out, which is the same thing. So the block moves twice as much as the pulley. Now so the block moves twice as much. This only moves half as much, only half the force gets through. Okay, so now what's the right answer? Going back to this clicker question. The votes are locked up. The right answer is on, I'll get there yet. Not A, not B, not C. I didn't quite get you to get the least popular answer, but the right answer is D. Right? This point has 16 times the acceleration of that one. 16 times. Okay. Now, what is the intuition mistake that many of you made, most of you made? And I will try to just get this straight in your head so you can think about it. Is that if you take one of these pulley systems, let's take this pulley system here. This pulley system looks like it's a good pulley system to help you pull things along. What happens is this is a system which multiplies force. If I have a force here, I have a tension here, I get twice the force on this thing. Any system which multiplies force and is passive attenuates motion. So this thing, it multiplies force and attenuates motion. The other one makes the force less and the motion larger. Unless you think hard and really get in the mechanics point of view, you will get confused between those two different concepts, which are reciprocals of each other. So they seem like the same cloud of ideas, amplifying the motion, amplifying the force. They're not. One is the reciprocal of the other. So one of these pulley systems makes the force bigger and the motion smaller, and the other one makes the force smaller and the motion bigger. That's one effect. The other is there's this extra factor, which is that the application point has even more of the same as the system itself. Well, I'll just leave it at that. That's where the square comes from. So anyway, good luck at the test tonight.